Today we've got Sabine Den Hartog talking to us. She's an associate professor at Heriot-Watt University, and previous to this, Sabine completed her PhD at Utrecht University and was a postdoc at both Penn State University and Utrecht University, and a research fellow at the University of Liverpool. Her research focuses on microscale mechanisms that control frictional behaviour of fault materials. This is applied to the context of geothermal systems, carbon capture storage, energy storage, and hydrofracturing operations. So please, Sabine, over to you. Take it away. Thank you.
Thank you very much, Lucy, and thanks very much for inviting me to give this talk. I will be talking about the microphysics of fault frictional behavior. Why are we interested in fault frictional behavior? Well, to understand that, let's have a look at this diagram. So this diagram shows a variety of geoenergy operations, such as geological CO2 or energy storage, natural gas extraction, or, and the most important one for everybody attending this talk, of course, enhanced geothermal systems. So all these subsurface energy systems, they affect the state of stress of the subsurface. And when there are faults present in the subsurface, then they can be reactivated due to this change in the state of stress. If there is a reactivation of faults, the movement along the faults can result in earthquakes or induced seismicity. Let's look at some examples of induced seismicity in geoenergy applications. So this graph here shows the injection pressure at the geothermal site in Basel in Switzerland, and it shows with the color codes, it shows the related seismicity. And the seismic activity in this reservoir increased with rising pressure and flow rate, up to the point that there was a magnitude 3.4 event in 2006. And this led then to the abandonment of the geothermal site in Basel in 2009. A more recent event was in Pohang in South Korea in 2017, and that was a magnitude 5.5 event, which was concluded to be caused by the geothermal system there. So this is also induced seismicity related to other geoenergy applications, so non-geothermal, like natural gas production in the northern part of the Netherlands, Groningen, which resulted in a magnitude 3.6 event in 2012, and that has led to the decision to stop producing gas in 2022, even though the reserves are not, there are still reserves left. For example, wastewater injection related to oil extraction can cause induced seismicity, or hydraulic fracturing, which occurred near Blackpool in the UK, which caused a magnitude 2.3 event. Of course, it's also natural seismicity, which for which fault frictional behavior is relevant. How can these geoenergy operations cause fault reactivation? Well, the key point is that in all the geoenergy operations, there's either injection or extraction of fluids at pressure. This here is the example of a geothermal injection well, so cold water is injected here, and that may then come into close proximity of fault zones. So the injection of that pressurized water, that can affect the state of stress in various ways. One of the ways, or the simplest way, is illustrated in this Moore column diagram, with the shear stress on the vertical axis and the normal stress on the horizontal axis. And the semicircle here illustrates the state of stress in the subsurface, and the lines here are the criteria which, once satisfy, cause movement along a fault zone. So when pore fluid at pressure is injected into a fault zone, one of the things that it can do is it can cause a translation of the state of stress towards lower normal stresses. So that then results in that the failure criterion is satisfied, and that can then lead to induced seismicity. The title of the talk includes microphysics, so that means that we're looking at microscale processes. Why microscales? Because faults are structures of many kilometers in scale. Well, but we know from observations in the field that the behavior in fault zones is actually very much localized along something called the principal slip zone. So that's indicated schematically in these diagrams here. So there's a very wide damage zone around or forming part of the fault zone. But the behavior is localized in this principal slip zone. And the thickness of that principal slip zone, it depends a bit what sort of material it consists of, whether it's cohesive in the case of ultracataclysite or incohesive in the case of gouge. But you can see that the slip zone thickness indicated on the horizontal axis here can be even less than 1 millimeter thick. So that's really very, very thin. So that means that to understand the fault scale behavior, we can actually look at what happens at the micro scale and even down to the grain scale to understand the behavior in nature. And that's what we will be doing. So I'll be focusing on phylosilicates in this talk. Phylosilicates, you may also know them as clay minerals. They are platy type minerals shown here with very long dimensions in two directions, so horizontally here and perpendicular to the screen, but a short dimension in this case the vertical sense. So this is a scanning electron micrograph of a selection or of a cluster of phyllosilicates, and you can see that they're platy minerals. And phyllosilicates, they are important because it's been observed that fault zones are very often localized along phyllosilicate rich surfaces. So to understand fault frictional behavior, we want to understand the behavior of phyllosilicates. The approach adopted consists of several steps. First of all, informed by nature, we perform experiments. Then we collect the experimentally deformed materials and look at the microstructures in them to understand the processes that occurred during the experiment. Those are then used to define a microphysical model, which is a collection of mathematical equations to describe the behavior of the fault gouge, and this can then be used by modelers to extrapolate the behavior to nature. Let's first look at the experiments. So for these fault friction experiments, we typically use fault gouge, and fault gouge, that's the crushed up material which lines the fault surfaces. It's shown in these diagrams with the red color. And the fault gouge is sandwiched between shear sliders, which can have a variety of different shapes. Those sliders, those forcing blocks, are then pressed together under a normal stress. And then one of the blocks is moved with respect to the others, which then causes a shear stress, or you need a shear stress to do that. So in this case, the central block is forced down, whereas the side blocks are supported, and you measure the shear stress needed to push the central block down. For the rotary shear configuration, one of the cylinders is held stationary, whereas the other one is rotated. In this case, you measure the you derive the shear stress from a torque, which is measured at distance. In the direct shear configuration, the entire assembly is shortened, and these two gray bits here are elastic materials, and the shear stress needed to do that is measured. So if you then divide this measured shear stress by the applied normal stress, you get something which we call the friction coefficient. It's indicated in mu. And that tells you something about the frictional properties of the fault gouge. So those shear sliders, they are located in a shear apparatus. And to explain it a bit, I will focus here on the direct shear configuration. So if we shrink that down a bit, the first thing that we need to do is to put a jacket around it. It's often some type of rubber, and we do that because the slider set is located inside a pressurized vessel, and the vessel is filled with often it's silicon oil. This is pressurized to apply the normal stress to the sample, and normal stresses of several tens to maybe even over 100 MPa are used here to simulate the conditions as they are in the upper part of the or under upper crustal conditions. Then usually heaters are placed around the vessel to increase the temperature during the experiment, and this will then this means that the experiments can be performed at in situ temperatures as well. And to actually generate the displacement of the sliders with respect to each other, the entire assembly is located inside a press. And for this press, the bottom here can move up at different velocities. And at the top here, you measure the shear stress with a load cell. So this here shows typical results from friction experiments like that. So this is the friction coefficient versus the displacement for the phyllosilicate muscovite under wet conditions. And the absolute value of the friction coefficient here, so absolute value of mu, that tells you something about the strength of the material. So how easy is it to reactivate a fault? In this case, you see friction values between about 0.3 and 0.6 or 0.7. And here it's dependent on temperature. So these are temperatures which are a bit more relevant for natural earthquakes rather than induced seismicity. If we now look at data which was originally, data produced by Moore and Lochner for experiments on several phyllosilicates at room temperature, the type of diagram is the same, so it's the coefficient of friction on the vertical axis and actual displacement on the horizontal axis. And what these authors did is they started deforming the phyllosilicate under dry conditions, up to 4 millimeter displacement. Then they introduced water, and then they continued with the deformation under wet conditions. And what you see, if we focus here on the solid line, which is muscovite, you see that when the water is introduced, so when the experiment is performed wet, the friction coefficient goes down quite a lot compared to the wet friction coefficient, and that's actually the case for all these different phyllosilicates. So water decreases the strength of the phyllosilicates. That is also shown in this diagram, which now shows the friction coefficient on the vertical axis and the relative humidity, so RH is relative humidity, that's shown on the horizontal axis. A relative humidity of 0 means dry conditions, relative humidity of 100 means wet conditions. And similar to the data that I showed to you previously, you see that the dry friction coefficients are higher than the wet friction coefficients. So this is a collection of literature data for different types of phyllosilicates at room temperature. But there's a decreasing trend of the friction coefficient with increasing humidity. Okay, so if we now go back at this typical example of results from friction experiments, you've probably noticed that there are these steps in the friction coefficient. Well, those are related to steps applied in the slip velocity, and they tell you something about the stability of sliding. So how likely is it that a reactivated fault will actually cause seismicity? So how do we interpret these steps then? Well, that's probably easiest by looking at these schematic diagrams. The top figure here shows the slip velocity. So you can see that there is a step in the slip velocity. So there's an increase in slip velocity. This bottom part here shows schematically how the friction coefficient responds to that step in slip velocity. So typically there is an instantaneous increase in the friction coefficient upon the increase in slip velocity, that is then followed by a more gradual decrease towards a new steady state friction value. So in this case, this new friction value, it is higher than the initial one. So with an increase in slip velocity, the friction coefficient increases. So the behavior here is velocity strengthening. This is quantified by this is a so-called rate and state friction parameter. It's A minus B. So it's these two parameters here. It's positive in the case of velocity strengthening behavior. When a material behaves velocity strengthening, you do not get earthquakes. There's also another type of behavior possible. So you see here that the increase in slip velocity is the same as in that case, but now the response of the material is different because the final friction coefficient is actually less than the initial one. So with an increase in slip velocity, the friction coefficient decreases. We call this velocity weakening behavior. The A minus B value in this case is negative, and this means that you could potentially get earthquakes. Another way of distinguishing velocity strengthening and velocity weakening behavior is shown with this diagram, which shows the friction coefficient versus the slip velocity. And as the name tells you, velocity strengthening behavior is a positive line, whereas velocity weakening behavior is a line with a negative slope. So let's look again at some phylosilicate data. So this is a pure muscovite gouge. It shows this stability parameter A minus B on the vertical axis and temperature on the horizontal axis. And what you see is that most of these values are positive. And that's something which is observed in general, that most phylosilicate gouges show positive A minus B values or velocity strengthening and stable behavior. That's also shown in this figure. So this is a different type of plot. It shows the friction coefficient on the vertical axis and the slip velocity on the horizontal axis. This is a collection of literature data for both muscovite or illite and biotite. What you can see is that, well, actually you can't see it that well because the axis here is a bit too, the scale's a bit big. But there are actually small positive trends in this data, which also means a velocity strengthening behavior, so that you can see that by the comparison with this example figure. Okay, so the next step in the approach would be to look at the microstructures generated by these experiments. So these are microstructures for muscovite on the left-hand side and biotite on the right-hand side. And what you can see in both cases is some sort of sigmoidal domains in which the grain size is bigger than around it. You can see that here as well, quite large grains in sigmoidal domains and smaller grains outside those domains. So the shear strain that you could accommodate by deformation only of these sigmoidal domains, because they're not connected, that's very limited. So they're not very likely to control the deformation. So it's more likely the deformation is controlled by what happens in the through-going finer grained shear bands. If we zoom in on those, then we see things like grains catching on each other, overlapping grain edges. So that, which obviously will provide some sort of a resistance to deformation. If we zoom in further on the grains themselves, then we see these grain ledges, so steps on the grain surface, which would also provide a certain resistance to deformation. Finally, if we, so the reference is falling off here a bit, but this is a figure from Kawai et al. 2015. So this is for muscovite, it's atomic force microscope image. And if you look at the cross section here, you can see that there's a nanometer scale roughness on this surface. And such roughness would also provide resistance to sliding. So the atomic scale is another scale we should take into account when we look at what processes cause the resistance to sliding. So this is now an overview of all these different scales at which the the interactions can control the strength of sliding of the phyllosilicate gouges. So this is a figure from the recent paper by myself and Dan Faulkner and Chris Byers, 2020 in JGR. As I mentioned, this large scale is not very likely to control the deformation because the strain you can accommodate is very limited. These interacting grain edges, they can actually control the strength, at least that's what we assume. So what happens here at the grain ledge scale, that is actually the resistance provided by those is very similar to the resistance provided by the grain edges. So we don't need to consider that one separately. And finally, the roughness at the atomic scale will also provide resistance to slip. So what we've assumed is that both what happens at the grain scale and what happens at the atomic scale, that those two processes control the strength of phylosilicate gouges. And if you look at this diagram, then you can see that to slide this grain any further, you need to overcome the resistance provided by the grain edge, but you also need to overcome the resistance at the atomic scale. So both of them are serial processes which we've taken into account. So the next step to understand fault frictional behavior better is to actually make a microphysical model in which mathematical equations describe the behavior as we've observed it. This includes, as I just explained, a serial process of a slip along the grain interfaces and overcoming the grain edge strength by cleaving off the grains or by cleaving off along the basal plane. So the first thing to develop this microphysical model is to quantify the microstructure, so to get expressions for the microstructural parameters. So the important one here is this overlap height C. And what we assumed in this model is that this overlap height is controlled by a normal compression of the aggregate under the action of the effective normal stress, so just by linear elastic processes. So it's related to the bottom here is the Young's modulus of the entire aggregate. So another important parameter is the size of the pores S, and that is related to the porosity. To then actually be able to predict the strength of phylosilicate gouges using this model, we need to look at an expression for the shear stress. So we assumed here that the shear stress is the sum of the shear resistance due to grain interface sliding, so the atomic scale processes, plus the shear resistance due to the grain edge barriers. So that's indicated, that's this part of the diagram is relevant for that. To actually get the, to solve this equation, basically, we need to get an expression for the normal stress at the edge, so sigma edge here. And to get that, we assume that there are basically two options. In under dry conditions, we assumed that it's critical crack growth of this edge crack, which is given by a Griffith type criterion. So it depends on the on the interfacial energy under vacuum. So, but when there's water present, then the grain edge barrier strength is actually controlled by subcritical edge crack growth or stress corrosion cracking. And that's indicated by this the classical rate law here. And you can see that there's the interfacial energy in the environment included here, so it's no longer the vacuum. If we combine these equations, and I won't go into the details here, but they can be combined to give you a relationship between the slip velocity, the normal stress at the edge, and gamma environment, so a parameter which depends on the basically on the relative humidity, on whether there's water present or not. So using that model, we could then make predictions for the friction coefficient. This is a figure that you've seen before. This is the friction coefficient on the vertical axis and the relative humidity on the horizontal axis. The symbols here are the literature data, which I showed to you before, and the lines here are predictions made with the microphysical model that I just explained to you. The different lines indicate different boundary conditions used for the predictions. And it depends on those assumptions what the absolute value of the friction coefficient is. But they are not too far off from the literature data, and importantly, the trend of a decrease in friction coefficient with an increase in the relative humidity is captured by this model. So if we now look at model predictions for the stability of sliding, so how the friction coefficient depends on the slip velocity, then again, it depends on the boundary conditions assumed, but the model predicts a small positive trend of the friction coefficient with velocity, which is also what was observed in experiments. So the model captures the velocity strengthening behavior typically observed in experiments for phyllosilicate gouges. So if we now relate this back to induced seismicity, so phyllosilicate gouges, both literature data, experimental data, and also the model predictions, they show velocity strengthening or stable behavior for these phyllosilicate gouges. So they don't seem to be related to unstable fault motion, but they're still important to understand both stable and unstable behavior, because they are part of other microphysical models, which are composed of a mixture of minerals. And those models, they do predict unstable behavior under certain conditions. So this here shows the temperature, which is equivalent to depth, and this frictional stability parameter on A minus B on the horizontal axis. Data here, so this is all data and predictions for mixtures of illite, which is phyllosilicate, and quartz. And these data points, they the data points are experimental data, whereas the lines here are model predictions. And this is a model in which there is both quartz and phyllosilicates. And you can see here that the model doesn't quite predict the positive A minus B values at the low temperatures here. Well, that is because this original model, which has been published several years ago, it did not include velocity strengthening behavior of phyllosilicates. So if we were now to incorporate the model that I showed you previously, which does predict velocity strengthening behavior of phyllosilicates, then this match should be better. So the final step in the approach would be to use these microphysical models to make predictions for nature, and that is something that modelers do. So just a little comparison between experiments and nature. Actually, sometimes we find remarkable correlation between both. So I will show you here an example of a study that I'm working on together with Marion Thomas and Dan Faulkner. So the observations are that the longitudinal valley fault along the coastline of Taiwan, that fault actually shows different types of behavior in the north compared to the south. The northern part shows, in the northern part the fault is locked, that's indicated with these dark colors. And in the southern part it's creeping, so slowly moving. So what we did in this study is we took 3 samples, so these are actually 2 samples very close together. We took 3 samples from the northern locked part and 2 samples from the southern creeping part, and we performed experiments on those samples. To our surprise, we found that samples from the locked section that they are stronger than samples from the creeping section, and they also show these pronounced peaks upon steps in the slip velocity. The samples from the creeping section, they don't show that. So there's quite a clear distinction between samples from the locked section versus sample from the creeping section. If we look at A minus B, so the stability parameter, versus temperature, then we also see the distinction between samples from the locked zone and samples from the creeping section. The color coding in this figure is the same. So the samples from the locked section, they are green and blue, and they actually show a decrease in A minus B with an increase in temperature. Samples from the creeping section, on the other hand, so the red and the purple symbols here, they show pretty much consistently positive A minus B values with temperature. And interestingly, the data which are inferred from geodetic analysis, so that those are the points here, they match very well with these experimental data. So we are still in the process of trying to understand this behavior, so the difference between the behavior of samples from the locked section versus samples from the creeping section. It seems that it might have something to do with the distribution of kaolinite, but yeah, that's still work in progress. So finally, at Harriet-Watt, we are currently investigating the frictional behavior of granite fault gouges. So that's part of the NERC-funded GWAT project. And this work is done by postdoc Nathaniel Forbes-Inskip and PhD student Nick Harpers. So the work is related to United Downs Deep Geothermal Power Project in Cornwall. So in this geothermal system, the injected water is so basically a permeable fault zone is used to for the water to move from the injection well to the production well, and we are investigating how those fluids, how they affect the composition of the granite. So that's shown schematically here. You could get a change in composition by fluids flow through. So we're looking at how the fluids change the composition and what the possible implications are for the frictional properties of the fault zone. Okay, so just to conclude, to better understand induced or natural seismicity, we need to better understand fault frictional behavior. We study that by looking at the grain scale processes, and we use a combination of experiments, microstructural investigations, and microphysical models microphysical modeling to understand the grain scale friction processes better. And those microphysical models, they allow for extrapolation of lab to nature. So thanks very much for your attention, and I'm happy to answer any questions.
Thank you, Sabine. That was excellent. Really, really enjoyed that. And it's so critical to the development of geothermal as we sort of scale up to these commercial productions. And I mean, I know I'm biased and from Cornwall, so I'm particularly interested in the stuff you're doing on United Downs. But yeah, carrying this forward, that work will be essential to make or break a project, really. So really interesting. Does anyone have any questions? Please just go ahead.
Can I ask a question?
Of course.
Great. Thank you, Sabine. Really, really interesting talk. I have a question about United Downs as well, as probably many people do. But one was actually about whether the research you're doing will evolve into looking at impacts on permeability across the fault zone, as well as just the impact on the friction.
We are looking indeed at the permeability as well. Yes, that's actually the experiments that we're performing at the moment, to look at the well, so far it's unaltered granites that we're looking at, but yes, we are measuring the permeability definitely.
Okay, cool. Thanks.
But I don't really have enough results yet to give any to share any of that.
Sure. I get what are the timescales of the outputs of that particular piece of work?
Sorry, was that a question or
yeah, sorry, that was just wondering what the timescales are when that work might be in a publication.
Okay. So obviously things are slightly limited at the moment, but we are doing lab work, and this year definitely, hopefully in the next not too many months.
Great. Cool, thank you.
Anybody else got a question?
I have a question. Well, first a comment. That was an incredible presentation.
Thank you.
Pleasure. I have a question about the mineralogy of the samples taken that in this slide actually that's up from the injection and the production depth. What the differences are.
So that's actually a question I can't answer myself. I don't have that data available to me. Actually, that's something that Lucy probably knows much better than me.
Sorry, was it the depths of the production well and injection well?
Yeah, the differences in mineralogy in those two samples that we're looking at.
Oh, I don't think those samples are related to the wells, are they?
This is just as an illustration. Yes, these are actually surface samples.
I see.
There was a fight over samples at depth, and there's only been a few cores taken in the production well in the zone of interest where the fault was, and they're currently being studied in Germany with the MEAT project. It would be great for Sabine to get her hands on some
Absolutely,
of them to compare them.
Well,
I just
hope
have a quick.
stands.
Sorry, I just have a quick question to follow that, Lucy. Are they whole cores or sidewall cores?
Sidewall cores, just a
Okay.
couple of inches. All right. Well, thank you so much again. I really like the work you're doing with Taiwan as well. That looks really interesting with the kaolinite, and it could be quite an interesting comparison with United Downs. So that
Yes.
that looks really interesting.
Yeah. Well, we should have the data all available quite soon.
Excellent. Cool. Well done. It's really, really good work, and yeah, very interesting. Please keep us updated as well.
I was just going to say there's a really interesting paper on silica buildup along fault planes that they believe has attributed to the induced seismicity at Pahang as well. I don't know if you've seen it or not, Sabine.
Is that a relatively new one?
I think it was last year or the year before. It was Rob Westaway, Neil Burnside, those guys.
Okay. I don't think I've seen it. I should.
I might have the paper somewhere. I'll try and email it to you because I helped them analyze some of the geothermal fluids from that well, so I'm sure I've got it somewhere. I'll dig it out and send it to you anyway.
Great, thanks. That would be good.
Cool. Well, thanks everyone for attending, and again,
can I ask another question?
Oh yeah, of course. Go ahead.
Yeah, sorry. It takes a while sometimes for the questions to come up. I guess more broadly, would the work that you're doing be able to identify higher risk and lower risk zones of seismicity across faults that are being prospected for geothermal development? And what kind of process, I guess, do you recommend to try to assess that risk? And then I guess during the drilling process.
So you're breaking up a little bit, so let me just see if I understood your question correctly. Whether you're asking whether we would be able to assess the risk of different sections of a fault zone? Or just different fault zones?
Just in fault zones, yeah. I mean, if you're looking, how much data do you need to actually collect before you're able to comment? At the early stage of exploration, when you're looking at different fault zones, and you allocate higher or lower levels of seismicity risk. And I know there's broad brush approaches, but I'm wondering if your research in particular has ramifications for that.
So I think that like the broad brush approach, I think that would be really quite tricky actually. So there are many factors affecting frictional behavior. So its composition is a main one, but it's also the normal stress, the pore fluid pressure, the temperature. Am I forgetting some now? Oh, well, those are the main ones. So you need to not only know exactly what the material is, you also need to know the in situ conditions along the fault zone and the state of stress. And if you don't know any of those, then it will be a guess, right? And it's I think the stress is really quite critical there, the state of stress. And also, and this is what we're trying to solve with microphysical models, to actually do experiments at exactly the conditions as they are in subsurface, or at exact in situ conditions. That is, well, maybe not totally impossible, but it's really, really difficult, especially if you don't know exactly what those in situ conditions are, right? But that's why we do the microphysical modeling, because if we understand the general behavior, if we understand the process as active, then we have more of a basis to extrapolate from lab conditions to natural conditions. Because if it's purely empirical data that you have, or that you would be extrapolating, you can't actually extrapolate it, right? So a lot of the data so far is still at room temperature, which is really quite there's a drawback from available data.
All right. Well, thank you again, and yeah, it's been a really good talk.
Thanks for hosting me.
Oh, it's a pleasure, absolute pleasure. Come back and tell us how it all went one day.
Yeah, I will.
Our next talk is on the last Wednesday of next month. And Helen, are you introducing that one?
Yeah, I will. So that's going to be Sean Watson from the University of Glasgow, who will be talking about his research on the influence of anthropogenic heat on the shallow geothermal gradient. So some of the stuff he's been doing in the shallow mine workings in Scotland as part of his research. So it should be a really interesting talk, and definitely a different take on the shallow geothermal picture.